It's a beautiful day here in sunny Santa Barbara, and I'm one day away from my first class at UCSB. But, I'm gonna let you in on a little secret. I gotta fire whoever picked the topic this week. Probability is darn hard to learn about, especially if you learn it incorrectly the first time around. But alas, I think I figured it out. Ever wonder how often 5 heads are flipped out of 10? No? Well, I'm gonna tell you anyways. First with examples, then with formulas. To start out, let's count outcomes. A die roll has 6 outcomes, 1 through 6. A coin flip has 2 outcomes, heads and tails. But if I were to roll a die, then flip a coin, there are 12 outcomes, 1 for every number in the die with heads, plus another 6 for the die rolls with tails. If you want a formula for the total number of outcomes, just multiply the number of outcomes for each event. It forms a table of sorts, 2 by 6, to get 12 unique outcomes. For repeated events, it's the same multiplication, but the total number of outcomes can be written with bases and exponents as well. Take the total number of options and raise it to the power of the repetition amount. Let's put it into practice now. How many unique outcomes are there in a 4-digit bike lock with 10 options for each digit? Well, 10 options raised to the 4th power is 10,000 unique outcomes. Now that's a lot of outcomes. What happens if the number of outcomes changes over time? Using the example of musical chairs, just how many different ways can a round play out? In a round with 4 people and 3 chairs, any of the 4 players can sit in the first chair. Once somebody sits, that seat is taken and that player is locked out of the other chairs. That means that there are now 3 players and 2 seats. Any of the 3 can take the second chair. After that, it's the same thing with the last 2 players in the final chair. Multiplying the number of possibilities, 1 chair at a time, gives 4 times 3 times 2, which equals 24 unique outcomes. If there was a round with 1 chair and the same 4 people, there'd be 4 total outcomes, 1 for each possible winner. In this version of the game, 3 people are left chairless. In a round with 4 people and 2 chairs, there are 12 outcomes, with 2 people left out this time. In reviewing the example with 4 people and 3 chairs, only 1 person is left out, and there are 24 unique outcomes. The number of outcomes seems to follow a factorial pattern, when more chairs are added. The only rule is that the number of people has to be equal or greater to the number of chairs. These musical chair type problems reflect a permutation formula. Don't worry though, the concepts that the formula represents are much more approachable than it looks. The formula just counts the number of unique outcomes in a problem where seating order matters and the people aren't allowed to sit in multiple chairs. You see, the top part of the formula counts the total number of outcomes with a full set of chairs, and the bottom part removes all the unused options if your specific problem has less than a full set. It really is that simple. Hey, here's another situation. I go to the store and buy 4 bags of groceries. When I get home, I have a few choices on how to bring them back in. I can only carry 1 bag in each hand, so I can carry 6 combinations of bags back in one trip. Bags 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. Not too bad. What if the bags are particularly heavy and I can only carry back 1 at a time? In this case, there are 4 different ways I can carry the groceries back. 1 choice for each bag. If the bags are light and I can carry 3 back at once, again, there are 4 options. An option for each possible bag to not take back. When I bring back either a small or large number of bags at once, there are fewer unique options than if I were to bring back a medium number of bags at once. These kinds of bag carrying problems reflect the combination formula. This formula counts the number of outcomes where order matters and I can't carry the same bag multiple times. Again, you don't have to worry. This big guy is just the permutation formula with one little variable added. The k factorial represents the number of ways a set of that specific size can be reordered. Adding the k factorial term on the bottom eliminates multiples of the same set, making that so order does not matter. Now that we know all that, we can really get to the meat and potatoes of this whole thing. Not just counting outcomes anymore, but calculating expected probability. Now just to make sure that we cover our definitions, probability is always a fraction of 1, with the number of wanted outcomes on top and the total number of outcomes on the bottom. Using our trusty old pal, the coin flip as an example, there are 2 outcomes, 1 for heads and 1 for tails. If I want heads, I have a 0.5 expected probability for that specific outcome. But what if I wanted to flip heads and then flip tails? This is where the multiplication rule comes into effect. Each event has a 0.5 expected probability, so if we multiply 0.5 by 0.5, we get an expected overall probability of 0.25. And, if anybody was asking, there are 4 possible outcomes. 2 outcomes times 2 outcomes gives 4, and out of the 4, only 1 is the desired outcome. So, the probability can also be found that way, 1 out of 4, which is equivalent to the result we got earlier, because 1/4 equals 25%. Another rule to remember is the addition rule. To find the probability of flipping 2 tails or 2 heads, add the probability of each event. 25% plus 25% is 50%. There's a 1 in 2 chance to flip heads heads or tails tails when flipping a coin twice. But what if I wanted to write the outcomes of the 2 flips a little differently? I can write each outcome as if it were a variable that can be multiplied. Then I can remove order as a distinguishing factor and combine like terms. The 2 outcomes with both a heads and a tails are seen as the same. Looking at another example with 3 flips, The pattern kind of resembles the process of binomial expansion. Interesting. But why does the pattern resemble the process of binomial expansion? Because it is. Looking at it from a more mathematical light, where heads is A and tails is B, is another way of looking at all these outcomes. Binomial expansion. In this analogy, the degree of the exponent represents the number of flips. In degree 1, there are 2 possibilities. Now say it with me, heads and tails. With 2 flips, there are 2 ways to end up with 1 heads and 1 tails, so that outcome has a coefficient of 2. This analogy is useful because, just like a tree diagram, every possible order and outcome is represented. But here's the important part. Like terms are combined. Looking at the pyramid, I can see that after 5 flips, there are 10 different ways to end up with 3 heads and 2 tails. Thing is, we already have a formula that does this exact thing for us, the combination formula. 3 choose 3 means that, out of 3 flips, all of them are heads. The function gives us the number of paths of that specific result, 1. 3 choose 2 means I flipped 3 times and got heads twice. The formula tells us that there are 3 paths to get that result. What if I want to get a little crazy with it and flip 10 coins? How will that formula hold up? 10 flips and 0 heads gives 1 outcome. Seems correct so far. 10 flips and 1 head, 10 paths this time. 1 for each flip. How about 10 flips and 5 heads? Showing my work here in the top right, there should be 252 different paths to get that result, the most likely of any of the combinations. Whoa, would you look at the clock? It's probability time. The 2 outcomes repeated 10 times gives 1,024 total outcomes. 0 heads out of 10 has about a 0.098% chance of happening, while 5 heads out of 10 has about a 25% chance of occurring. Okay, I think we can move on. What about a situation where one event was more likely than the other? Let's say I can crack eggs without shells in them about 80% of the time. How likely am I to make a shelly omelet? This is where the binomial distribution formula comes into play. In the formula, uppercase P sub x is the probability of an event happening with x number of successes. N is the number of trials, and P is the probability of an individual success, while Q is the probability of an individual failure. The formula works by using the multiplication rule of probability on the right side and multiplying it by the number of combinations, where the desired number of successes occurs. Not actually that bad. Using the formula, there would be about a 29% chance of making an 8-egg omelet and having 2 of the shells of my eggs tag along. And another situation. Last one though, I promise. Say that 20% of phones have Instagram, while 10% of phones have Snapchat. Using the multiplication and addition rules from probability from earlier, 2% of phones would have both apps and 30% of phones will have either app. But that doesn't seem quite right. I know plenty of people that have both apps. Well, the stats say that the odds of that should be pretty darn low. This all changes if we add the information that the apps are dependent and mutually exclusive. Say that if a phone has Instagram, it also has a 40% chance of having Snapchat. The somewhat to scale graph shown on the right shows Instagram in red, Snapchat in yellow, and both in orange. Okay, to find the probability of having the related apps Instagram and Snapchat on a single device, there's a formula. Multiply the probability of the dependent event by the probability of the event that it depends on. We know that the probability of having Snapchat given Instagram is 40%, so Instagram is the event that Snapchat depends on in this scenario. The probability of having both Instagram and Snapchat, also known as the intersection of Instagram and Snapchat, is 8%, much higher than if we were to use the multiplication rule, which only works in situations where the events are independent and mutually inclusive. If I wanted to find the percent of phones that have either Instagram or Snapchat, I would need to add their individual probability and subtract their overlap, in order not to count that area of the graph twice. We already found that 8% of phones have both Instagram and Snapchat, so after adding the corrective term, we found that 22% of phones have either Instagram or Snapchat, a bit lower than if we were to use the addition rule, which only works in situations where the events are mutually exclusive. Okay, review. To find the probability of both events, A and B together, you can multiply the probability of each event, or multiply the probability of one event by the dependent probability of the other event. Which one you use depends on whether the events are dependent or not. To find the probability of either event A or B occurring, add the probability of each event, or add the probability of each event, then subtract the space where they overlap. Which one you use depends on if the events are mutually exclusive or not. Now time for review problems. Let's start with this one. How many ways can 8 people finish an 800-meter race, where order matters? If you need some time to think about it, it's okay. Just pause. Okay? Time is up. The answer is C, 8 factorial. Next question. How many unique sets of 3 can place on the podium in an 8-person race? This is a problem where the order on the podium does not matter. I'm just asking for the number of possible sets. Okay? Ready? The answer is D, 8 factorial. divided by 3 factorial times 5 factorial. This is a combination problem. They use factorials plus an extra term that removes multiples of the same set. This next question isn't that bad. What is the probability of flipping heads, heads, tails in 3 coin flips? I'm going to give you a second to pause. The answer is A, 1/8, the same as every other possible combination of 3 coin flips. The next question asks, what is the probability of flipping at least 1 tails in 3 coin flips? Another second pause. The answer again is A, 7/8. This one involves using the binomial distribution formula along with the addition rule. Or alternatively, you could just count the options in your head or even on your fingers. Okay, get ready. Last problem now. Given that the information that 20% of phones have Instagram, 10% of phones have Snapchat, and the probability of having Snapchat given Instagram is 40%, how often does a phone have Snapchat but not Instagram? I'd recommend pausing now because I'm going to give away the answer in a second. The answer is D, 2%. This problem involves taking the total probability of a phone having Snapchat and subtracting the section of overlap where both phones have Instagram and Snapchat. There you go, 2%. Oh my goodness, that was a long one, folks. Thanks for listening all the way to the end. And remember that the mitochondria is the powerhouse of the cell.